Hi, I'm Matt with Schematical, and today I've got a guest. Kartik, would you care to introduce yourself?
Sure. I'm Kartik Sreenivasan. I used to be a software developer for Adobe Systems back in Bangalore, India, and then for the last 5 years, I've been doing my PhD in computer science at the University of Wisconsin Madison. Um, I've been working primarily on optimization and machine learning, and most recently, kind of disentangle all these fun properties of large language models.
So, this will probably be my only in-person interview with anyone. And we're enjoying a relaxing beverage as well, so this may make the cutting room floor, but we're going to find out. So, Kartik, I specialize in Amazon Web Services and running stuff at scale on the internet, in the cloud, if you will. So I am going to ask you, with those large language models, how do you guys run them? What hardware do you guys run them on?
So I think the first thing to disentangle that or clarify is who we means. So if we means me as a PhD student in academia, it means me running it most of the time on tiny little gaming GPUs that we have on our own clusters. That could be like 3080 Ti's. We typically run with NVIDIA because so far they've just been better and more economical.
So what you're saying is I should buy NVIDIA stock. I'm just giving you a hard time.
Unless it's already hit a ceiling, which I have heard rumors of, but I don't believe it because every time someone says NVIDIA has hit a ceiling, they just get better. So I don't know.
This is not a financial channel.
Nope.
We do not give financial advice. I was just talking tonight.
I give terrible financial advice, so don't listen. But that's what academics typically do. We also tend to run experiments on the cloud. Now, the fast pace of machine learning means that back when I started my PhD, which was not that long ago, back in 2018, when we ran stuff on NVIDIA V100s, we thought we were getting really, really good performance, and we'd spend a bunch of money on it, and we would hit our budgets really, really quickly. But in 2023, when people are training GPT-4, which has an estimated 275 times 8 billion parameter model, it basically means that V100s are just not going to cut it. They're ridiculously slow. You need a bunch, and when I say a bunch, I mean a huge number of NVIDIA A100s or V100, or H100s to even get going, which an academic budget will not get you. Also, when you spin stuff up on AWS, it means you're going to have to get a huge number of nodes, which are not necessarily in the same server farm. So communication between them is going to be slow. So if you split a model across those, your performance is going to be pretty bad. So when I say we,
hi, the royal we.
If I end up saying like where I did my last summer's internship at, which was Mosaic ML, which then got acquired by Databricks, we typically either have our own GPUs on our own clusters, or we acquire these from service providers like AWS or CoreWeave or OCI. And then you have a bunch of co-located GPUs, which are much, much more easy to use.
Okay. Have you ever used SageMaker? AWS SageMaker?
Not actively. If I do that, it's I am abstracted away from it. So I am typically working at a higher level of abstraction. So I'm usually like either just like actively building models or like researching even like models at inference at some point. So I typically don't go to that low level unless I'm in academia. So in academia, I don't use SageMaker. I just use EC2 instances directly.
Okay. Pause here. She just has to go outside, and I've got to reward her since she's using the buttons.
A few moments later.
Oh, good puppy.
And the channel, if they follow me, they actually know these guys. So Teeling was just in the video I rolled out yesterday because he wouldn't get off my lap. I think I inhaled the hair.
Oh, God.
I'm going to edit this all out. All right. So, you're not making this easy, man. You're eating my thumb. I use "so" as a filler word. I say that all the time. So
That's a reasonable filler word. I feel like filler words are important. Large language models use filler words too. That's the thing.
Okay, let's go with that one. Hold on. All right, we're back. And in the intermission, which I might edit in anyway, he just told me large language models use filler words.
Yeah, because large language models basically are modeling language that they have seen on the internet, right? And it's impossible at the number of tokens, which are like of the order of trillions for large models, to like filter out these tokens so they're all good, meaningful tokens. So actually, different models just have different behaviors in terms of conciseness. So if you typically have base models, which are also called foundational models, just like GPT-4 base or whatever. And then you have these models that fine-tuned to be instruct models, which is what you typically want. You want a model that like you ask a question and it gives you the answer. Doesn't try to just complete what follows the text. So for example, I ask a question like, hey, what is the capital of Wisconsin? Right? Now you ideally want the answer, Madison. But the large language model doesn't know you're asking a question. It just saw a bunch of text and it was trained on a next word prediction objective. More specifically, it was trained on a next token prediction objective, which means all it knows is it saw these characters and it's going to predict what's the most likely character to follow it. Now, if it figured out that you asked a question which typically falls in a sequence of questions, like maybe there's like a nice little quiz which it was trained on, which was what are the different capitals of the states in the United States, that it would first say what is the capital of Wisconsin. It would follow that up with Madison, and it then would not output an end of sentence token. It would go on to then say, okay, what is the capital of Texas, which is Austin, Dallas?
Austin. It's Austin.
There we go. And then it would go on to go to the capital of California, it would say Sacramento, and it would keep going.
Mm-hmm.
So this model, for lack of a better phrase, would not know when to shut up.
Mm-hmm.
And also, because it was trained on regular natural language, I have seen models which will then go on to just like blabber nonsense. Like it will behave like I did back in undergrad when I was trying to write an answer and try to appear smart. So I just use a bunch of clever words which aren't really meaningful, and then go on to say a bunch of stuff. And eventually, this is the most hilarious thing that happened to me a couple of months ago, actually, where I was figuring out why a model was stopping mid-sentence. And the best theory I ended up figuring out was the model would start saying stuff, eventually start spewing nonsense, at some point figure out that it's spewing nonsense and be like, oh, I should shut up, and it would stop talking. So this would be like an instruct model. Another very common variant of these models, which are all trained from these base foundational models, is a chat model. This is a model that you typically use. ChatGPT, which everyone uses, is a model that's designed for conversation, which is what in NLP people would call multi-turn conversation, where I say something, it gives me an answer. I then ask a follow-up question on that answer, and it builds that context and replies. Whereas an instruct model is not designed for that. An instruct model is designed for give me a task and I will perform it, and then I stop.
Okay. Curious. That's interesting. It kind of reminds me of when I was in college and I was attempting to woo mates at the bar late into the evening and blabbering on until I realized I was blabbering on. Luckily, with YouTube videos, you can edit that out. I wish you could do that in real life.
Oh, God, that would be fun. I would edit a lot of sections of my life out. But then again, I feel like I've enjoyed the blooper reel in live.
Yeah, fair enough, fair enough. All right, so recently I tried writing a LLM search engine. So I written web scrapers before, search engines, sharded indexes, all sorts of fun stuff there. And I wanted to use an LLM to ask it if this was relevant. So there was a short search criteria I was looking for, and I combed the page and I found all these links and all the text areas that were kind of grouped together, and I sent them into the LLM and said, listen, here's an array of all the different, let's just say, names of like text in the links that is human readable on the page. Give me the one that most likely has to, give me the index for the one that is most likely to do with pricing. So I gave it an array and I said, give me the index in that array. Now it couldn't figure out what that index was, which makes perfect sense. And actually, in hindsight, I was doing it like a fool, but I should have asked it to give me the text back of the one that was most likely to be used for pricing and then just done a text compare, which makes a lot of sense right now. I don't know what I was doing there, but you had an idea that it's bad at math, right?
Yeah. So okay, a lot of things to unpack here. Let's start off with the last one, which is bad at math. And actually and shameless plug here, we have a paper on teaching arithmetic to small transformers, which...
If you send me the link, I will put it in the show notes.
Sweet. So we put that paper out on Archive a couple of months ago, and the motivation behind the paper was I prompted ChatGPT, so GPT 3.5 at the time, with like a long integer addition question, and it got it wrong. And I was like, this is surprising. This is a model that like people are using for like really, really complicated tasks. And it's playing Minecraft on its own. It's writing beautiful prose. And for some reason, it can't add like 7-digit numbers. This is off. And then like I corrected it. I told it like, hey, you've got your addition is off by 1. Fix it. And it said, sorry, I know I made a mistake. Here's the fixed answer. And it got it wrong again. And then I yelled at it a couple more times, and eventually it got it right. So the takeaway from this is, while these models are great at what we think are complicated tasks, they're getting simple tasks really, really wrong. And the reason is it doesn't know that it's doing addition. It never learned the algorithm of addition. And this is the main takeaway from the paper, where we found that like you can actually train a really small model to do addition fairly well if you explicitly train it to do addition. And just like one of the key takeaways was something as simple as flipping the digits improves the quality of addition significantly, flipping the order of digits. And the reason is, if you think about how you do arithmetic, you do it from the least significant digit to the most significant digit, because you carry on each operation, right? Mm-hmm. But if you ask an LLM to output the answer, it's a decoder-only transformer, meaning that it outputs characters from left to right. Mm-hmm. So it's outputting the most significant digit first, which means it had to do the whole addition first, throw away the remaining digits, output the most significant digit.
Okay.
And then do the same for the next and the next and the next, which is much harder than computing the least significant digit first. And this led to a fun little paper, and then the little paper ended up asking a lot more questions. So we did a bunch more ablations, which then led to 50 pages of scientific experiments on Archive. So take a look at that if you get the chance. Main takeaway from that is simple things like arithmetic is hard even for massive large language models. Now, why is this important? Why this is important is because what we think are simple tasks are not simple tasks in the next token objective regime. So what I mean by that is adding two numbers is as simple as adding two numbers. I can train a one neural network to do this. This is effortless. If I set the weights as 1, it just adds the two numbers. I'm done. But that's not the space in which large language models are working. They're working in the token space. Now, what a token means is I take a word or a sentence and I break it up into chunks.
How many letters in a token are?
Excellent question. It depends on the tokenizer.
Yeah. Okay.
So a very simple tokenizer is just a character level tokenizer.
Okay. So each individual, like A, B, C, each letter is its own token.
Exactly. But this is 1, inefficient. And 2 is not capturing dependencies. Mm-hmm. So for example, if I model ing as a dependency, as a single token, I can use the meaning of ing in both the word running and walking, and it means the same thing there. It takes a verb, run/walk, and turns it into a continuous tense.
Okay.
So doing this is beneficial. Now you could do this in a very bespoke manner, which is what some tokenizers like Spacey do, but this doesn't scale. So what people do is use something called a BPE, which is a byte pair encoding style tokenizer. So what you do is you basically take all possible character combinations and then see which ones are most likely to co-occur and make those into tokens.
So it's bytes. You're talking about like you take it and put it to like an encoding, not ASCII. I assume,
Exactly.
Like UT, and then you look at the all right.
Exactly. So
what are those chunked into then? What is a UT?
The end result you don't know. So they're chunked into like arbitrary pieces. But eventually what you get is a vocabulary of tokens, for lack of a better word. Some of those could be meaningful. They could be like ing. They could be like the letter S as like turning something into plural. They could be digits. But then if you look at like the GPT-3 tokenizer, for example, it will tokenize things kind of weirdly. Like for example, like if you look at the number 123, 123, it'll tokenize them into 12 and 3. And then you look at the number 1234 and it'll tokenize that into 123 and 4.
Okay.
So it's not smooth.
No, that's not that. No.
And
not.
Also learning addition in this space is now pretty messed up.
Okay.
Because if I have individual digits, I know that when one is in the position of this thing, it always behaves the same way. But the model never sees the 1 in 1234. It sees 1, 2, 3. It sees 123. So it's got to learn addition in a really, really tough space.
Yeah.
And that's harder. So this simple problem of addition, which we teach kids with this simple iterative algorithm, is no longer simple in the token space. They still learn it though, because like you give this model enough data, it just consumes knowledge and then it knows how to spit it out. But it's not reliable. So in our paper, what we found was if you trained a model on 3-digit additions, it got really good at 3-digit additions. It didn't know how to do 4-digit additions. If you train a model on 3-digit additions and 5-digit additions, it still didn't know how to do 4-digit additions because it learned what it saw.
Mm-hmm.
And it's very hard to see whether the new thing you're asking it is something that it has seen before. So when you asked it to fetch an index of something that's very similar to what it was provided, it didn't know it was looking for an index. It was not solving that problem in like a divide and conquer way where it broke down the original problem into saying, I'm going to find which sequence is the most similar and then give you the index of that. Like that would be 2 sub-problems, right? Mm-hmm. It doesn't know how to do that. So what you ended up encountering was a problem what people in the LLM world refer to as prompt engineering. Because if you ask it the same question in a different way, it will give you a different answer. Because for it, that's a different problem. Mm-hmm. So one of the simplest ways, this was like the miracle of chain of thought, was people started just querying models on mathematical problems by saying it, okay, so they asked it a specific mathematical problem and it got it wrong. And then they said, hey, take a minute, take it step by step. Now it would do the same mathematical problem, but it would provide you the intermediate steps. And all of a sudden, the accuracy just shot up.
Really? I could see that. Because then it's got the previous steps, all the work in the middle to kind of build on. God,
exactly. And again, another shameless plug. We have another paper which is going to be appearing in Europe's 2023.
Send me the link.
Called Dissecting Chain of Thought, where we basically proved exactly this, that like if you break a function into its constituent components and specify the individual steps and thoughts, turns out it becomes much, much easier to learn. So varying your prompt in that situation, which like you mentioned, could be asking it for the text as opposed to the index. Fun story. I've I've heard this from colleagues, and I've tried this myself on several models. Hyping up the model actually works pretty well. Where if you tell the model, hey, you are a world leading expert in doing this task. Here are a couple of examples where you crushed it, where this was the input, this was the output, this is the input, this is the output. Now do the task, it gets a lot better. This being the input, being the output, giving these examples is something called in-context learning, where the model seems to learn from samples which are given to it within the prompt. This is something that's actually pretty phenomenal. This is what people call an emergent property.
It's kind of cutting edge right now, right?
Exactly. It's an emergent property of these transformers, because until now, models had a fixed input size. They didn't do any learning in the forward pass. Right? If you had a neural network to learn anything, it would be in the backward pass where it computes gradients. There's this wonderful paper by Garg and Chipras on what functions in context, transformers learn in context. And they basically showed that transformers can do linear regression, which is like given an input vector X and an output W transpose X. So that's like some unknown vector W. It can then do linear regression, meaning identify what that W is and apply it to an unknown, to a new test sample, X test, just in the forward pass. So what I mean is I give you X1, Y1 is the output, X2, Y2, X3, Y3, where each of the Ys is W transpose Xi. And now I give you a new unknown X test, and it does W test transpose X test.
Now, I can see that if you fed in the context of like A plus 24 equals 25.
Yeah.
And B plus 1 is 2. You know, but then how would that work with something more complex like solve world hunger? A is people are hungry, B is they need food. I don't know.
Excellent question. So here's the fun part. Right? So I think the good part about of the Garg and Chipras paper was that they broke it down to a very simple setting, which is numbers, vectors. We know what we're doing.
Gotcha.
When you break things down into these higher order concepts, it becomes complicated. So one thing that large language models even today are not good at is telling you what they don't know.
Okay.
It's very bad at saying, I don't know this, I'm not confident about this answer. It'll try to output something anyway.
Hallucinations is a term.
Bingo.
Yeah.
That's exactly what they do. And hallucinations is just like a widely extensible term, which I recently found out might have been like proposed by Karpati in some blog, Andre Karpati. But the main takeaway is like hallucination could be as simple as its addition being off by 1. It hallucinated it. Hallucination could be as serious as you ask it some problem and it says, hey, refer this book by XYZ author. The book or the author doesn't exist. It just made it up. It does that stuff all the time. But basically, this whole problem of in-context learning is that if you showed examples, so there's this wonderful paper which came out by OpenAI a while ago called GPT. What did it say? I think it was, correct me if I'm wrong, but it's something like GPT-3 is a few shot learner.
I'll add it in post.
There we go. So there's a few shot learning paper which basically took GPT. It was the GPT-3 paper. That's what we call it colloquially. And it showed this few shot property, which was that if I gave a model a task, say correcting typos, I happen to misspell cat as CBT, and I happen to misspell dog as DPG because I'm picking the letter that's right next to it or something like that. And if I just ask it to fix a typo, it doesn't know what to do. But I give it a bunch of examples where I said CBT actually refers to cat, DPG actually refers to dog, and then I asked it a new question like HPRSE, what is this supposed to be? And it will say horse. Well, I wasn't able to do that before. Now, if you think that the model is actually learning how to fix typos in those examples, That's probably not the case because 3 examples are too little to do that. And that's where the linear regression paper really shows it, because you need D examples to at least solve D linear equations. But what it might actually be doing is it might be saying, I know how to fix typos. Just that I didn't know in the first question that you were asking me to fix a typo. After seeing 3 examples of typo fixing, I now know that's the problem you're asking. So now I know how to solve it because I always knew how to solve it. I just know that this is now what you're actually asking me.
Mm-hmm.
So that's...
It changed how you ask the question.
Exactly. And so in context examples is like a fairly good magic trick where if you have a pre-trained large language model, just give it a couple of examples of what you were trying to do and it'll do better. The catch being, this might not always be economical because you have to fit these examples into the context length. And what if your example is really, really long? What if it's like, I have 100 lines? Let's say my example is as simple as identifying the missing number.
Mm-hmm.
But each example has 1,000 numbers. This is going to just fill up my context length. And if I'm using like OpenAI API calls, that's going to be prohibitively expensive.
Do you think it's a race to the bottom? You think that this is going to get more expensive, this arms race? Do you think it's going to get cheaper?
First of all, I'm a PhD student. I started off in optimization. I feel like I am more focused on the mathematical problems. The economics of it usually escapes me. But considering that there are so many new open source models coming out, like I interned for a company called Mosaic ML, which put out some really, really high quality open source models. There was MPT-7B, there was MPT-30B. Facebook's been has been putting out their open source models, Llama. There have also been some new models, Falcon.
I tried using Llama recently.
And these models are difficult to fit on GPUs for sure because they're big.
Yeah.
And most like commercial, like most like users like you and me who just have one GPU at home are going to find it difficult to even inference them. But that said, I doubt they will get more expensive because everyone is trying to make inference faster and faster. And with open source models, which does seem to be the future, everyone's going to be able to host these models on their own. So if OpenAI starts saying, I'm going to make GPT-5 or GPT-6 or GPT-7 absurdly expensive, people will just say, I'm just going to go to somebody else who has the technical know-how to like set up a nice little AWS cluster. Host one of these open source models, which is not as good as GPT-6 or GPT-7. Because I'll tell you that it's an unfortunate truth, but like OpenAI is still ahead. GPT-4 is bloody good. So these models may not be as good, but you could like host them for a fraction of the cost. So I doubt they're going to get more expensive.
All right.
And people are definitely focusing on the inference regime. So like I said, so far we've only talked about using these models as they are, not training them to do something new. If you use the models as they are, all you have to do is what they call inference. And that is actually much easier to make cheap because you can do some things like quantization. So what I mean is like if you have 16-bit numbers in the weights, I'm going to make them 8-bit, I'm going to make them 4-bit, 2-bit, whatever. That's going to make it significantly cheaper. I can also like batch process inputs. So like if multiple people are sending me requests, I'm going to like package them together and then influence them together. There are research works on this. There are tools to do things like this. And this will definitely become more and more efficient. I think that's just a matter of time.
You were describing so many things that we are doing on the back end of my Stable Diffusion product. So I love it. I'm glad we're on the same page. I do not have a PhD. I am nowhere near a PhD, but I'm glad that we're somewhere in the neighborhood here.
I don't have a PhD yet either, but hopefully soon.
I'll still call you Dr. Kartik. So let's talk training data. So a lot of this data is crawled from the internet.
Yep.
Is most of your data crawled from the internet? Is part of it like privately, collected from students? Like especially this question and answer stuff. I mean, are we just like crawling GitHub issues and what's the other one? Stack Overflow.
So excellent question. Now this really is what I think is the magic of large language models. I went into my internship thinking I'm going to figure out what is this big secret that makes GPT-4. There's got to be some magic here that's unpublished and doing some crazy stuff. And honestly, my takeaway from it is one, the engineering problems are really, really hard. So academics typically don't care about engineering problems. We care about more of the mathematical problems. We care about architecture, algorithm problems. But we don't think like the engineering is actually that difficult. Like, hey, these are matrix multiplies followed by nonlinearities. You just scale them up. Turns out when you start hitting a really, really large number of parameters, these costs of even like moving the model from RAM to GPU RAM to the cache within the GPU, those times start being really, really expensive. So you have to do really good engineering to make sure you don't do unnecessary transfers, you don't do unnecessary computations. And so I will caveat what I'm going to say with saying that the engineering is very, very hard. OpenAI has done a fantastic job about it. The Mosaic ML platform is phenomenal. They did some really, really good work there. But once you've got all of this sorted out, the miraculous performance of large language models, in my opinion, seems to be almost as simple as good tokens in, good tokens out, which means if you have a lot of good training data, you get good models. If you have sufficient number of parameters and sufficient amount of compute. Now, where do you get this good data? In OpenAI's case, we don't know. Because as much as their name is OpenAI, they haven't told us where they do these things. With a lot of Mosaic's models, the ones that are commercially licensable, the data came from commercially licensable sources, open source data sets. So a lot of it, like you said, is crawled from the internet. There are these data sets like C4, MC4, which you can go pull off Hugging Face. AI2 recently released this data set called Dolma, which I think has like 1 trillion tokens, maybe more, which is very high quality data. So they did a bunch of work on deduplication, which means that like if you crawl from the internet, you're going to get a bunch of identical samples, right? Because multiple websites will have the same thing. And you won't know this while crawling it. While you're scraping, you just scraped and collected a bunch of data. These are like 1 trillion tokens of data, terabytes of data. You're not going to know that like 2 samples are going to be the same, or 100 or 1,000 or even 1 million samples are going to be the same. And if these samples are the same and then you train on it, you have basically skewed your ratio now. Like I thought originally I'm going to have a uniform distribution over, I don't know, addition, multiplication, and subtraction because I care about all of them equally. But because of these clones, maybe I have a whole bunch of addition examples and very few multiplication examples.
Let me put that in a layman's terms. So I with the Stable Diffusion stuff I do, we do dog photos, not nearly on the same level. Imagine if I uploaded 8 of the same photos and then 2 that were diverse. I'm trying to train Teeling's face into the model.
There you go.
I have 1 photo 8 times and 2 that are of him doing something besides the first photo. Okay.
Now what's going to happen is the model is trying to minimize loss. So obviously it's going to try to get a perfect prediction on all 8 photos. Or we're doing 10, I think it was 8 and 2.
8 and 2.
8 and 2. So it's going to try to get the minimum loss and try to perfectly predict all 10 pictures.
So it overtrains to the 8.
But what it'll end up doing is because it's easier, it'll perfectly predict the 8, which is really easy because for 1 I get 8. I'm going to say I don't really care about it too because I get 80% accuracy anyway. So it might end up stopping there.
Okay.
And so the problem is if you don't deduplicate, you have a bunch of clones in your data, and now you're telling the model it's an easy way to get really good accuracy. So you got to deduplicate, and this is what the AI2 folks, Alan AI, did with Dolma. So you have a bunch of data sets like this, and this is typically what people use. Now that said, if everyone trained on the same data, everyone knows the architecture, everyone has the same models, most people are going to get the same results, but that's not true. Meta gets different results, OpenAI gets different results, Mosaic gets different results. So what's the sauce? The sauce is that once you have these open source data sets, which there are plenty available if you have compute, you then say, I am going to apply my own cleaning and filtering process. And yes, it is actually that quote unquote dirty, where you have to get your hands dirty, go into the data and say, I am going to clean this data up, where I'm going to say, I have a bunch of Stack Overflow answers, and for some reason, I believe that the top 3 answers are good and the rest of the answers are garbage. I want to only keep the top 3 answers. Some people are going to say, I'm going to keep all the comments. Some people are going to say, no, I don't care about the comments. The comments are nonsense. When you're scraping Wikipedia, so these C4 data sets already have scraped a bunch of these websites, right? They've already scraped Wikipedia, they've already scraped Stack Overflow. Maybe the scraping went bad. Maybe they picked a bunch of really stupid divs.
Mm-hmm.
So like all of a sudden, my model, when it's trying to predict what the answer for write me code to reverse a linked list, it's going to start printing Stack Overflow divs, which would look really, really ugly to the user.
Mm-hmm.
So maybe I'm going to go and clean out div tags. So this kind of cleaning as not sexy.
Sorry,
Hey, Shay.
I have a hungry dog here. You can wait. It's not even dinner time, girl. Calm down.
So cleaning data doesn't sound as sexy as designing a new transformer architecture.
That's something you give to like an undergrad.
In our lab, we end up doing all our dirty work ourselves usually.
Wow.
We give the fun problems to the undergrads so that they get excited to do research and then convince them to do PhDs.
Gotcha.
But
then you give them the dirty work.
But my current take of it is doing these kind of things actually is what gets you your good performance. So you can get your training data from the internet. This is what a lot of people do. There's also a bunch of stuff which I didn't mention at all, which is called RLHF data. It's
RLHF.
That's reinforcement learning with human feedback.
Yep.
So it's called preference data. So what that means is like getting actual answers to things is difficult, but it's easier to get answers on like whether a given answer is good or bad.
Mm-hmm.
So if you look at ChatGPT, a little while ago, they added this like thumbs up, thumbs down button, where once you get an answer from ChatGPT, you can tell it whether the answer was good or bad.
Yep, I've done that.
And that's data that OpenAI then takes back
Mm-hmm.
and uses to train their RLHF model, which then helps them generate new data.
Mm.
Because now, not only do they have the data that they trained on, they also have a new data of saying, my model did this and it worked, and my model did this and it didn't work. You can then feed it back into the model. So you get a bunch of data like that. This is data you can again generate. There are also just like organizations that will sell data.
Yeah.
So you have that too.
Yeah, there's money in data.
There you go. Put all that together, and I think that's where you get your training data. But if you're someone who's just starting off and wants to get their hands dirty, I would say go on Hugging Face data sets, pull up C4, MC4, pick a chunk of it that seems reasonable to you, and then start messing with it.
All right. Wow, I am impressed with your ability to stay on task right now. I was like 6 questions away there. I want to jump back to the hallucinations. Did you hear about the hallucination that happened with this? There was an attorney. Like, not a tech guy, who put in to ChatGPT to write his opening arguments, and it hallucinated a whole bunch of precedented cases.
Oh God, I don't know about this, but I believe it.
I'm pretty sure he's going to get disbarred.
Oof.
So, just a side note there is, I'm pretty sure, be careful with those hallucinations. All right. So I'm going to jump back to where you were talking about spreading around your training to different nodes. So in the business and tech, that might be referred to as sharding. So
bingo,
okay, you've got it as well. Can you shard models for LLMs?
Excellent question. And if you had asked me this like 3 or 4 years ago, I would say yes, but it's really, really hard.
Okay.
So most of you, I hope, are probably using PyTorch. I tried using TensorFlow, but I found it hard. So I stuck to PyTorch. PyTorch was easier for me to use easily, get started. When you want to split a model across GPUs, there are 2 ways to do it. One's called data parallel. The other's called model parallel. Parallel, yeah. When you use data parallel, what you do is you have to do forward passes and backward passes over a batch of data.
Is this during training or during inference?
For now, let's say training.
Okay.
If you want to do a forward and backward pass over, let's say, a batch of 64.
I guess, if you're going backwards pass, it's obviously training. I'm sorry.
Let's say 64 examples, whatever. They could be images, they could be text pairs, whatever. That example, 64 examples. The easiest way to do this is to have a model copy on all of your GPUs and just fit as many examples in each GPU as possible. Let's say each GPU only fits one example. I have 64 GPUs. I can do 64 forward passes, 64 backward passes, and then I aggregate the gradients.
That's some beefy infrastructure right there, 64.
I don't know the numbers that OpenAI has to run GPT-4, but trust me, it's more than 64.
Okay. No, I mean, on AWS, you can boot up a damn near unlimited amount. I'm
but
just saying.
They wouldn't be co-located,
That's
which would give you a
true.
bunch of grief. But
I can boot them up in the same VPC. I don't know. We can find out how much I can spend in one day.
there you go. So they get expensive really, really fast. So let's say this is 64, right? So now I do forward pass and backward. But each model exists fully on each GPU. This is what they used to call data parallel. Easy to execute on using PyTorch, using like a wrapper called distributed data parallel. So you just wrap this class around your model now and just show it your GPUs. It'll do the rest.
Okay.
What if your entire model and your optimizer does not fit in one GPU? Then this doesn't work anymore. So this is where people used to do something called model parallel. What you can do is you can put some layers into one GPU, some other set of layers in other GPUs. They're like, I'm going to do a forward pass on these layers on these GPUs. Take that intermediate output, send it to the other GPU, let that guy do the work, and meanwhile, this guy's working on something else.
Well, that's interesting. I've never seen it split into layers like that.
Now that's very hard because when you do this, you start getting into problems like stale gradients. Also, it's very hard to implement. The orchestration becomes kind of difficult. Also, when your models become really, really large, what kills you are not the model weights or the gradients. What kills you is actually the optimizer's state dict. So while you're doing this training, your optimizer, typically let's say Adam or Lion or whatever, is going to have variance estimates for each and gradients and current weights for each of the weight parameters of the model.
So if you had it stored, let's just say you had the layers stored across 3 different machines, GPUs, right? Would they have to be run on the same instance or same server, or could you run them on separate servers?
So you can run them in separate servers. The problem is when you talk between the servers, if they're not geolocated, that's going to be really, really slow.
That makes sense. So what if we had 100 layers, 100, the first 100 layers of nodes as one layer, I guess. They get another 100 and another 100, right? So the first one you'd send it inputs and it would process and then have outputs, and then it would send outputs from that to server 2 that would then run those through its GPUs. It's 100 layers there, and then it would send that to the third one. And then when you went backward propagation, you'd have to do the same thing backwards, huh?
Yeah. And this is what makes this whole thing complicated. And back, I don't know, I think this was in 2020 or something, when I was taking a course in Madison, we read this paper called Pipe Dream.
Pipe Dream, that's great.
It's a
great
fun
name.
title.
Pipe Dream.
Which was doing this whole model parallel and pipeline parallelism. And
Shay, don't gnaw on your sibling.
it was a complicated algorithm, and it seemed very, very hard to get right, because this gets very tricky very fast unless you're willing to have all the other GPUs just waiting while these guys are processing their inputs, which you can't do. That's just wasting money, right?
Yeah,
So you have to pipeline all these things, and this is why it becomes complicated. And this is why for the longest time people didn't bother. People said model parallelism is not something that is easy to implement, so we're not going to do it. Let's just do data parallelism. Until very recently, PyTorch released this framework called FSDP, which you mentioned the word sharding. It's called fully sharded data parallel. And what it does, and I don't understand this completely yet, it also happens to shard the model and the optimizer state dict across GPUs. So now, almost as easily as you could split the data across GPUs, you can also split the model across GPUs. So if you have enough, you still eventually need enough memory to on each GPU to hold the model, but like eventually, what you can do is you can say, I have 16 GPUs. You are allowed to split even the model across these GPUs. Go ahead, share them as you like, and I will, from a programmer's perspective, I'm going to treat it as though I have one GPU and one model. And PyTorch will just handle away all those complicated interactions and abstract it away for me. So fully sharded data parallel, lifesaver.
Okay.
It wouldn't be possible to train these really large models easily without it. You would have to write the code to do that, and it gets complicated really, really fast.
Okay. Well, worth looking into. All right. I don't want to cut us off. I think we're killing it. I think you should have your own damn podcast.
You're asking phenomenal questions, man. And I would say, tell your friends, listen to this podcast more. I'm having a lot of fun being on it right now. I'm also having a lot of fun watching these puppies fight.
I feel like I could have you as a recurring guest because we're just scratching the surface here, but I'm going to try and wrap it up so we can get them fed and whatnot. So I want to give you the opportunity to talk about the future. Where do you think this is going? And one thing that pops in my head is, have you done any work with quantum computing at all?
Okay. So let me answer the second question first, because that's an easier answer. Quantum computing, no. I know almost nothing about it. I've heard a couple of talks about it, and it blows my mind. I recently discovered that like these qubits are stored several levels below the surface because they have to be kept at like 2 Kelvin.
Yeah, it's almost zero, yeah.
Which blows my mind, because like I thought absolute zero was just like unattainable. Like it was just like it's an incredibly expensive and impossible process to keep, and this is why there are so few qubits in the world. But turns out like if you have it even at like a reasonable temperature, let's say 50 Kelvin or whatever, these qubits become very unstable. So you have to keep them very low. So they're very expensive. That's all I know about them. Quantum computing is a whole new game. I'm not even going to comment about it. In terms of the future of LLMs and AI, I'm
Get over here.
I'm excited, honestly, because I recently discovered, and y'all can try this out as well. GPT-4 can write really, really nice raps. Like I was having fun with a friend in a coffee shop, and I was like, I want to make this model write a rap about you. And like I gave it a few lines about him, and I was like, write a rap, and you can be explicit if you like. Being explicit, by the way, was a difficult thing for large language models because these models were something called AI alignment, which basically means we're trying to make these models safe. We don't want them to like be like have bad behavior, like swearing all the time and stuff like that. Because like I remember one of the famous models a while ago. Eventually, if you like start pressing it on certain questions, it would like start making like death threats, and you don't want that. So eventually, you try to make these models nice and calm, and Meta overdid this with the Llama model, where like that model got aligned into being fairly useless, where you asked it a question, it would just, for reasonable questions, it would just say, as an AI language model, I'm not allowed to answer this. So this is what a lot of people started saying, Meta lobotomized the model. So you don't want that. So being able to be explicit while not being dangerous is actually a difficult problem. And somehow GPT-4 did this because that rap was good. It sounded fun. It had all the points that I wanted it to have.
I've heard of summing up things in like the voice of Tupac and whatnot. It's
there you go.
Yeah.
So that's some very, because that's hard. I don't know a lot of human beings who can do that well.
I don't know of any. I feel
There
like
you
in
go.
high school a bunch of guys tried, but
Right?
Yeah.
And yeah, oh god, that brings back some memories. But
shake.
all right, the dogs are getting antsy, huh?
The dogs are getting antsy.
So I'll wrap this up real quick. The answer is I was very impressed by this,
Okay.
and I don't see these models getting worse in time. I in fact see them getting better, which means my take is a lot of tasks that we currently do, these models will get better at doing, and so we'll just have them do them for us, which means we'll be free to spend our time doing other things or more complicated things and just use them as tools. Do I see them doing the whole Skynet take over the world thing? Not anytime soon.
That's the thing. I just don't put them in charge of the nukes. Please.
Yeah. Like they spit out text. Let them continue spitting out text.
All right, so we're gonna wrap it up, but I will bring up one way they might demise our civilization. And we don't have to go into this right now. AI girlfriends is a topic we were talking about at dinner. And AI significant others of any type. That might be the end of mankind. But I'm gonna leave in the comments. Please let us know if you think which is more dangerous: the Skynet killing us with nukes, or us just. You ever see that episode of Futurama with the AI?
I did not.
Insert clip of that here.
But I would say don't get an AI girlfriend. Go to a bar, talk to a girl, say hi.
Maybe not a bar, but yeah, better places to meet your mate. But all right, with that said, Kartik, it has been a pleasure and an honor, sir.
Likewise.
I would hope we would do many more of these. We could do like a monthly segment. I got a feeling you're going to be like the star of the show. Well, these guys are the star, and then you're the co-host, and I'll just be a distant background figure.
No, you crush it. Looking forward to it. And you got to insert this somewhere. My opinions are my own. I don't represent UW-Madison or my lab or any of the companies I spoke about. So.
And we've had some beverages. So.
Cheers.
Cheers. I'm like I'm empty here, but cheers. Had one drop left. All right. That's a wrap.